Good morning. We will continue with our discussion about the thermoelastic problem that we did last time. So what we covered last time was the equation, the strain displacement equations. The way they appear when the thermal strains are involved are as given here. So whenever you are having thermal strain, in addition to the regular equation, so this is the relation between epsilon x and the stresses in the three direction. An additional term alpha into delta t appears in this equation, and the shear strain displacement equation, they don't have any change except the displacement and the linear strain equations are different. Using these equations, we derived a condition where a body is purely heated. So there is no constraint. If it is allowed to heat, allowed to expand or contract freely, we expect no stresses to occur. And we proved that using these equations, indeed we get sigma x equal to sigma y equal to sigma z equal to 0, and tau x, y, z are automatically 0 because they are unaffected by the thermal load. So that is a simple proof that we have done. Today we will use the same equations to prove another simple case, that is, rather than heating a body with no constraint, we will constrain it fully. So we have this pen, you enclose it fully inside a box such that it cannot expand and increase its temperature. So what do you expect to happen to this particular pen? Stresses will be induced in this particular plane, and they will be tensile or compressive. There will be compressive stresses because the pen is trying to expand, you are not allowing it to expand. But in this case, there is one additional thing. I am not only constraining in the x direction, but I am also constraining in the y direction and in the z direction. So it is, this volume is not allowed to expand at all. So what do you expect to happen in sigma y and sigma z? Means rather the 6 stress values, what do you expect them to be? So that is what we try to find out using this set of equations. So these are the set of equations. Remember that in thermal stresses, the shear strain and shear stress, they are unaffected by the imposition of temperature. So whether you enclose the body or free the body and then increase the temperature, the shear strains and shear stresses, they will not exist because the uniform temperature rise will not cause any distortion. So as a result, these stresses will remain 0 even when we expand in the constant state. The condition that we are trying to analyze is a body which is uniformly heated and fully constrained. Fully constrained means you are having ux, ui and uz, all three equal to 0. So as a result of this, you will automatically get that epsilon x, how do you represent epsilon x in terms of ux, ui, uz? What is the relation between epsilon x and ux? Del u by del x. So that is the relation. So since ux, ui, uz are 0, the epsilon x, epsilon y, epsilon z as well as the shear strains all will be equal to 0. So once these shear strains are 0, the shear stresses are automatically 0. So that we already have predicted. Let's see what happens to this first set of equations. So we know that since there is no expansion allowed because of fully constrained, epsilon x is 0, epsilon y is 0, and epsilon z is also 0. So this implies that epsilon x equal to epsilon y equal to epsilon z equal to 0, as well as the gamma values, but I did not write it there. Now we are interested in finding out what happens to sigma x, sigma y and sigma z from this calculation. So let's write the equation. So the first equation you can write as sigma x minus mu times sigma y minus mu times sigma z plus E alpha delta t is equal to 0. What I have done is epsilon x is 0. I multiplied by e to the both sides. So we have 0 equal to sigma x minus mu sigma y minus mu sigma z. And then you have plus alpha delta t multiplied by e. So E alpha delta t equal to 0. So that is what we get the equation. Similarly, we can write the remaining equation. So we will get minus mu times sigma x plus sigma y. So we get these three equations. After rearranging the terms, we will get the equations as this. If you subtract first two equations, we get 1 plus mu times sigma x minus 1 plus mu times sigma y equal to 0. So if we subtract the first two equations, we will get sigma x minus mu times sigma x, that is sigma x plus mu times sigma x. The second is minus mu sigma y minus sigma y, so that is 1 plus mu times sigma y, and the other terms, z term will get cancelled. So this will imply that sigma x equal to sigma y. Similarly, from equation 2 and 3, so if we subtract 2 and 3, you will get sigma y equal to sigma z. So it implies that all the sigma x, sigma y and sigma z, they are equal in magnitude. So that is the conclusion we have got. We will substitute this condition into any of these equations and we can find out what is the value of the sigma x, sigma y and sigma z. So I am substituting this condition in the first equation. So I will get sigma x minus mu times sigma y is now nothing but sigma x. So mu times sigma x minus mu times sigma z. So sigma z is again sigma x plus E alpha delta t equal to 0. We get the value of sigma x as minus E alpha delta t divided by 1 minus E. And this is nothing but sigma y and sigma z as well. So what conclusion we draw matches with what intuitively we thought earlier. So what we thought, if you don't allow the body to expand and if you are hitting it, it will undergo compressive stress. So that is what we got. So sigma x, sigma y and sigma z, all of them are compressive provided delta t is positive. Delta t is positive means you are hitting the body. If you are pulling the body, then everything will be tensile. And 1 minus q nu, this factor we did not anticipate. If you just constrain in one direction, then you will get the stress is E alpha delta t. Because of the Poisson effect, because we are constraining the remaining two dimensions as well, we get this Poisson effect or Poisson term comes in this particular equation. And that is the condition that we get for this simple case. So more complicated cases, the more complicated cases will involve the temperature gradient where a body is having one temperature at one point, another at another point, and then you are providing some constraints. So those type of complicated problems are not part of this course, but here you will get an exposure or idea as to how do you handle thermoelastic problems. And two simple cases that we have seen in the previous lecture and this lecture illustrate how to use the basic governing equations from which one can start the stress calculations. Any questions on this point? So let's proceed with a new topic. till now our discussion has been always in terms of what is the stress or what is the resistance in terms of force and what is the deformation. So we were looking either stress or strain in order to check whether the body is safe or it is not safe. So that was our approach. Today we will learn another approach which is an important. So one particular situation where this stress strain approach doesn't give quick result or the present mechanism or the equations that we have studied, though they don't yield immediate result, is a condition such that suppose something falls on this table. So this something heavy object falls on this particular table. What is the deformation and what is the stress that are going to appear in this particular table? We cannot predict using the theory that we have been learning till now. So in such cases, we have to use what is called as energy methods. So whenever you apply any load onto a deformable body, so solid mechanics deals with all the deformable bodies. So whenever you are subjecting a load to any deformable body, it deforms. And here we are dealing with elastic bodies. So as soon as we remove the load, that body comes back to its original shape. So bodies, all the bodies, including this table, will behave as if it is a spring. So whenever I apply some force onto this table, it will deflect. Provided it has not gone in plastic range, once we remove the load, the table will come back to its original position. So why it comes back to original position, we can relate to its modulus of elasticity, and that is one approach of looking at this particular problem. The another way of looking at it is whenever you apply load on this particular table, whether because of the falling load or a simple uniform load, I am just pushing with my finger. What happens is this particular body, it will start absorbing whatever work is being done on this particular table. So when I am pushing my finger pushes the table down. So in this case, the finger being softer, the finger gets pushed. Means you can visibly see the finger getting pushed. So this deflection of the finger is where my muscles or the material inside the fingers, they are absorbing the energy in the elastic range. So as long as the fibers, that is my muscles don't break, they will absorb that amount of energy, and as soon as I remove the load, I lift the finger, my finger takes the original shape. So what brings these deflected muscles to the original shape is the energy which is stored inside it in the form of what we call as a strain energy, and that is what we are going to study in this today's topic. So whether it is a table or a finger or whatever object, whenever you apply the load, the work being done during the application of the load is getting stored in the form of strain energy inside that particular body. As long as the material remains in the elastic range, it is capable of relieving that energy after the load is removed. So if you apply the load, the body will deflect. If you remove the load, the energy which is stored, it can be immediately relieved by that particular body. So that is the idea. So whenever a load is falling, you can calculate by using the equations of dynamics how much energy you are supplying. And once you know the energy being supplied, we require some set of equations which will tell us a body which deforms by X amount, how much energy is stored in that particular body. So if you have a rod which deflects by 1 millimeter, so this plane, if it is deflecting by 1 millimeter, how much energy is stored in this plane, we require some kind of equation. Once you know the equation, and if you see that a load falls on this plane and this plane deflects by 1 millimeter, we know that what is the effect of that load is in terms of the energy. So if we know what is the energy that is being applied on this pen, we can predict how much is the deformation of the pen, and hence the stresses those are induced in the pen. So that is the approach that we are going to discuss today, and that is called as the energy based methods. It is very powerful method because the only way to easily handle dynamic problems or impact problems. So some body hits another body, so that is very common phenomena. So how to predict stresses in these cases is given by this particular method. So first, in order to do these calculations, we need to have an equation which tells us, given a certain amount of load, how much energy gets stored inside a body. So here we are talking the mechanism by which the energy is stored inside the body. Just like the stress and strain are abstract constraints, so that we are talking about, whenever you apply the load, the stress gets generated. So stress is nothing that material knows, that is only in our head we have an abstraction that material resists it, and the resistance can be measured in terms of stress. The resistance can also be measured in terms of how much energy that material is capable of storing. So if you exceed that energy, the material will break. So rather than saying that stress exceeds the yield stress and the material yields, we can say that the energy exceeds certain critical energy and the material yields. So those two are the different ways of looking at the same behavior of the material. Material as such doesn't know all these theories. So these are our understanding of the nature of the material behavior. So the second approach is the energy-based approach. That is what we will develop some set of equations and then we'll solve some problems using this particular method. Okay, so we'll first understand a situation rather than the impact situation, which is more complicated to understand. We'll understand a simple situation. We are considering a rod which is originally of length L. So the BC is the original rod and it is being slowly pulled by applying a force which is given by P. So as you start pulling this particular rod, it expands, and at particular load P, the value of expansion is given by X. So if you plot the load versus the stretch or the elongation of the body, you will get graph something of this form. So the y-axis is the load, x-axis is the elongation of the rod. So as the load increases, the elongation keeps on increasing. Now since we want to look at this problem as an energy problem, here in this case we can calculate the energy which is being supplied to this rod, that is the material, in terms of what is the work being done by the external force. So if the external force at this instance is P, or it is constant P which is being applied, and it is stretching it by a distance x. So the displacement is x. So what is the work being done when you displace a force by x amount? So Px. So the force multiplied by the displacement gives us the work done. Now where does this work goes? This work goes inside the material in the form of the energy stored in the material, that is called as a strain energy. So strain energy is nothing but the storage of the work done by the external forces when they act on that particular body, that gets stored inside the body in the form of energy which we call as a strain energy. Why strain energy? Because the body visibly deforms whenever you apply the load, and deformation and strain are the analogous concepts. So we call this energy as energy related to deformation of the body or the strain energy of the body. So that is the concept of strain energy. Now how do you calculate what is the total work being done when you have the load displacement diagram is shown here. So let's say at particular instance, so this instance the load is P and the deflection which is happening, that is the incremental displacement which is happening, is given by dx. So at this instance the total work which is done by the external force will be given by Pdx. So the work which is done during the displacement by dx will be given by the load multiplied by dx. So here P is the instantaneous load which keeps on increasing over the time or over the displacement range. At this instance, the load is P, and assuming that for a very small time the load remains constant and the displacement happened as dx, the work done will be given by P multiplied by dx. The total work when we are deforming the body from zero load to the maximum load, so let's call at the maximum load the body has deformed by displacement x1 and the load let's call it P1. The total work would be addition of all those incremental steps. So we can consider from zero load to the maximum load, all these small strips are getting added. So when the load is zero, you will have this much work when there is a small displacement. When you further increase the load, another amount of work will be added. So if you add up all those work done, you will get the final total amount of load which is being supplied to this rod and which the rod will store in the form of strain energy. So if you want to know the strain energy, it will be given as addition of all those strips, which mathematically we can write it as integration of dW. So that is P multiplied by dx. So that is the total energy stored, which is called as strain energy inside the body. Okay, and the limits of this integration is the total elongation. So dx x runs from 0 to x1. From x equal to 0 to x1 is the total amount of work which is done by the external force, which will be stored as a strain energy inside the body. This particular approach expresses the load in terms of the external load. What we are interested in terms of the internal forces or internal stresses, that is what we will translate this equation in terms of the stresses in the next step. At this stage, we will understand in terms of the external load. Later on, we will convert this in terms of internal stresses. So when the load, this is the general equation and it geometrically represents, so this integration geometrically represents the area which is below this particular curve. So this is the load displacement diagram. The total area from 0 to x1 below the curve is given by this particular equation. If you consider a case of linear elastic material, so what we see here is a general behavior. So what we see here, initially the material is elastic. So let's say from here to here the material is elastic. So in the elastic zone, this particular area below the curve can be easily calculated by directly the geometric equation. So if I call this as x1, so rather than this being x1, I am in the elastic zone where the region is x1, which is a straight line. So what we are interested in finding out is the area of this triangle which lies in the linear zone. So this is P or P1. Then the area below the curve will be given as half times P1 into x1. That is the area of this triangle. So for linear elastic material, the strain energy will be given as half P1 into x1. So is this clear? So to summarize, what we have done here is given a regular body such as a rod which is subjected to axial pull, we can calculate what is the energy stored under the action of that load by this particular body by a general equation which is integral P dx. And for a linear elastic body, that means if this rod doesn't go in plastic zone, it will be given as half P1 into x1. So if you know what is how much the rod has expanded by 1 millimeter under the action of 1 Newton, then the energy stored will be half into 1 multiplied by 0.01 meter. So many joules is the energy which will be stored in this particular rod. Now this particular formulation gives us the energy, but mostly in engineering we would like to convert all this into stress form. So we need to convert this equation into stress form of the equation. That is what we are going to do next. So we would like to convert this equation in the stress form. For that we define another term, so that is called as a strain energy density. which is represented by symbol small u. So strain energy, total strain energy in a component is given by capital U. The strain energy density is defined as the total energy which is stored in the body divided by volume of the body. So strain energy density is density per unit volume. So the unit of this would be joules per meter cube or joules per unit volume. So we'll use this condition to convert this equation into a strain or stress and strain based equation. So we'll write the equation. So capital U or rather small u will be capital U divided by volume. So that is integral P dx divided by volume of a body. So here we are considering a body which is a regular body. So we are considering a rod-like object which is having a cross-sectional area A. So let's say this rod has got cross-sectional area A and it has got length of L. So the volume of this body will be given as A multiplied by L. So we'll use that condition. So we'll use A multiplied by L. So we'll take this A and L inside the integral. So we'll write this as 0 to x1, x running from 0 to x1, P divided by A and dx divided by L. So that is the form we are writing here. Now what is P divided by A? Force divided by area. That is the stress. So we have integral stress multiplied by dx divided by L. Now here x is the elongation. So remember that is x is nothing but delta L. So what we are talking x is the delta L. So when we are talking about, so we can write the strain in terms of x divided by L. So as x is equal to delta L, we can write strain as x divided by L. So we can write the same equation. So we can write d epsilon, that is a change in the strain, would be given as dx divided by L. So we can write this dx divided by L as d epsilon. So the rather than integrating over the displacement, we are integrating over the initial strain and the final strain. So initially we are considering no load condition. So the initial condition x is 0, displacement is 0, that means strain also will be 0. And whatever is the final strain will come as the limits of this particular integration. So this particular form of equation brings the energy formulation into the or in terms of the stresses and strains which we are interested in. So we will be simplifying this particular equation so as to predict the stresses. So what we are interested is whenever somebody falls or you just hit this particular rod by some force, how much stress will be generated in that particular body. So we are considered here gradually applied load, but later on the basic formulation of the energy equation remains same, whether the load is gradually applied or it is impactfully applied. The internal energy storage will be given by the same equation as given here. So this form of equation is the basic equation from which we will develop further. Okay, so is this clear? So we have defined two concepts here. One is the U, capital U, that is the strain energy which is defined for a full component, and another is energy density. So energy density is energy density at a particular point. So that is energy per unit volume. So the capital U will be for this entire table. So on this table, if some person is standing, then each point, that is the table top, the legs, everything will be undergoing some stress, and every component, the legs, table, everything will store the energy. The total energy stored will be the capital U. whereas this energy will not be distributed equally in this particular table. The tabletop where the person is standing below the legs, there will be some strain density, that is the strain energy density. Away from that, here there will be load strain energy density. In the legs, there will be another strain energy density. So this energy distribution inside this table will be different, and that difference will be predicted by the stress. So wherever stress is highest, the energy density would be highest. So let's say below the legs of the person, the stress is highest. The strain energy density below the legs or below the application of the load would be highest. Away from that, let's say the stress at this point is less. The strain energy density at that point also would be less. So that is what we are talking here. So here is, the integration is not in the space or in the geometry, but it is over the time. So from zero load condition to full load condition, we are calculating how much energy is getting stored in that particular body. So we'll simplify this particular equation for a specific case. So in this course, we are only dealing with linear elastic material. So for linear elastic material, we can express stress in terms of strain. So we'll simplify this equation for linear elastic material. Okay, so let's say I want to simplify this equation for linear elastic material, and the clue is that we know the stress in terms of strain. So can somebody suggest how we can simplify this equation, means how we can calculate that integral for linear elastic material? So we are integrating with respect to d epsilon. So that means whatever term is there, we have to express in terms of epsilon. So what is stress in terms of strain? It will be E times epsilon. So we have stress divided by strain as E is given by E. That means the stress is E times epsilon. So we can now solve this integral. So remember that whatever we are doing is for linear elastic material. Luckily, most of the engineering problems that work in the regular domain, we always ensure that they are in the elastic domain. So all this formulation will work for most of the cases. For very critical conditions, we intentionally cross the elastic limit in order to maybe minimize the weight or to optimize some conditions. But this particular simplification that we are doing, luckily is valid for many of the real life problems, and hence we are studying it. Okay, so U can be written now as 0 to epsilon 1 U times epsilon d epsilon. Again, we are considering that material does not, the E value is constant, it does not changes. That means the stress strain curve is a straight line, there is not non-linearity. So E can be taken out. So this integral will become epsilon square by 2 with the limit 0 to epsilon 1. So the strain energy density would be given as E multiplied by whatever is the final strain up to which we want to calculate the energy, and written as this form. Typically we don't use this subscript, we call whatever is the maximum strain induced, square of that multiplied by modulus of elasticity divided by 2 will give you strain energy density or energy per unit volume at this particular strain. Wherever that point is of this particular strain, the density would be given by this particular formula. Usually one is not interested, most of the times one is interested in stress. So the usual practice is to express this equation in terms of stress. So we just write the epsilon in terms of stress, and U will be E times stress divided by E, the whole square by 2. or mu is given as. So this is the form in which we are going to use the equation. So both are formal, means both are correct, but the more common format in which the strain energy density you will find in the books would be, it will be the stress square divided by twice the modulus of elasticity. So that is the strain energy density. So this is, remember that this is not the total strain energy, but this is strain energy density. Okay, so we have reached to this particular step. Before we proceed further, we'll look at some of the definitions, which are some of the terms which are used in the energy-based methods. Before we proceed further and take some simple cases for which we can calculate using this particular formula, what is the energy content in some simple geometry. Okay, so just now what we have seen here is strain energy density is given as the integral of stress into with respect to the change in the strain. Physically what it represents, so this is nothing but the area below the stress strain curve. So whenever you do the tensile test of the material, you will get this stress strain curve. The area below the stress strain curve, whichever strain value you are interested in, is nothing but the strain energy density. So the physical meaning of the strain energy density is whatever strain you are calculating the density at, whatever the area below the stress strain curve, till that strain value is given as the strain energy density. So this particular area is nothing but the strain energy density till the point epsilon 1, 0 to epsilon 1. So we are integrating 0 to epsilon 1, sigma into d sigma. So that is the area below the stress strain curve. That is the physical meaning of this particular case. And we just now derived for linear elastic material, the relationship just before this we derived is given here. If you want to know what is the total energy in the rod or in a component, you have to multiply this density by the volume, assuming that this density is equal everywhere. If it is unequal, the rod is having different cross sections, then by different section by section, you have to calculate total energy. When you will take numerical problem, that will become clear. So total energy would be given in terms of the energy density multiplied by volume of that particular component. Then some of the terms which you will find in the textbooks or in while discussion about this particular method, the energy absorbing capacity of the material is termed as resilience. So you will hear the term resilience, which is nothing but the energy absorbing capacity of the material. So just like we talk about the stress, which is the load bearing capacity of the material, force per unit area, the term which is used to measure the energy absorbing capacity of the material is called as a resilience. So when you hear the material is more resilient, that means the material is capable of absorbing more energy. So in that way, this resilience term would be used in solid mechanics. So in terms of what, it is ability of material to absorb the energy. So more resilient material means it will absorb more energy. And usually it is used for the purpose of discussion in this class, we are using this term till the elastic limit only. So that means the material absorbs energy and it is able to fully give out that energy because it is within the elastic domain. So that is what is resilience means. There are few more terms, like you have the term yield strength and ultimate strength in the stress domain. In the energy domain, there are two terms. One is called as the modulus of resilience. So this is the maximum strain energy density that a particular material can carry. So that obviously depends. If you remember, the strain energy density is given by sigma square divided by 2E. Since sigma can go highest value of sigma in the elastic limit is up to yield strength. So this is the stress strain curve of the material. The linear region of this particular material is up to sigma y. So the maximum energy which a material can absorb would be given in terms of sigma y. If you calculate that, it will be sigma y square divided by 2e. Our earlier formula was sigma square by 2e. The maximum value of sigma is sigma y. So sigma y square by 2e is the maximum energy which the material can carry at any point of time. Not maximum energy, but maximum energy per unit volume. And that particular term, the maximum energy per unit volume a material can carry, is termed as modulus of resilience. So that is just a terminology. Another term, so this is material property. Just like yield strength or ultimate strength, you may find in some data sheet the modulus of resilience is given as so many joules per meter cube. So that means that is the energy carrying capacity, maximum energy carrying capacity of the material. Whereas the proof resilience is the term which is used for a component. So this is the energy per unit volume, maximum value. This is the energy a total component can carry. So for example, if this pen is subjected to axial compression, till the time it yields, how much energy the entire pen can hold inside it, that is called as a proof resilience. So proof resilience would be for a pen, for example, a pen-like object, whereas the modulus of resilience would be for the material of this pen. So this, whatever is synthetic material is there, so that material, how much energy per unit volume it can carry is given by the modulus of resilience. If you multiply it by the volume of the component for a simple component, then that will give us the total energy capacity of that component, which is called as a proof resilience. So that is the two terms which you will find in the literature or in the textbook. So that you should be aware of. We will apply this particular method to calculate the strain energy content for some simple cases before we proceed for more complicated situations. So whatever we have learned, the summary of that is the strain energy density is given as sigma square divided by 2. So that is the summary of whatever discussion we had. If you have to remember one formula, that is this formula that you will have to remember. Now using this formula, you have to prove that this particular rod, which is subjected to load P, it can carry the total, so capital U means total energy content of this particular body is given by this particular equation. So that is what we want to prove. So can somebody tell how do we proceed from this equation to this equation? So first we have to move from U to capital U. So what is, this is energy per unit volume and this is the total energy of this rod. So what is the relation between capital U and small u? U multiplied by volume of whatever body we are trying to work out. So the left hand side of the equation at least we are able to anchor. So let's proceed. So capital U will be given as sigma square by 2E multiplied by volume of this particular rod. So this particular rod has got cross-sectional area A and it has got length L. So what would be the volume of this rod? A multiplied by L. Now, how do you proceed further? You want the equation in this form. So there is no sigma here. So how do you bring it? We have to write stress in terms of force per unit area. So then P square by capital L. So that is the equation that we wanted to prove. So this is the equation which we always, so any energy problem, this is the starting equation based on which you can proceed further. So this problem is clear. So energy density to total energy, you have to multiply by the volume and then simplify in terms of the load. Now let's take a case where the cross section of this rod is changing. So how do you calculate for that situation? So earlier case, it was a rod of uniform cross section. Now the rod has got two parts. One is the larger area. The larger area is given in terms of some coefficient n square multiplied by area of the smaller section. The area of the smaller section is capital A. That of the larger section is n square times A. And the smaller area is up to length L by 2 and the remaining L by 2 is with larger area. And again the load of P is being subjected. Okay, okay. So how do you proceed with this? Again our equation is strain energy density will be given as capital U divided by the volume. That is number one. So these are the two equations that we have. So in this case, there are two cross sections. So earlier case, we could calculate U multiplied by total volume. So we cannot use that kind of approach here. So how do you do this particular part? So we know how to solve the problem for a rod of uniform cross section. So in this case there are two uniform cross sections. So we break the problem into that of two uniform cross sections. So we'll write the total energy as energy of first cross section. So let's call this as first cross section and this is second cross section. So U1 plus U2 The U1 would be given in terms of the strain energy density of the first part. So it is small U1 multiplied by volume of the first component plus U2. So this particular part has got strain energy density U1 and it has got volume V1, where it is U2 and V2. So at this stage we don't know values of them, but that for writing the equation I am using them. U1 and U2. Okay, how do you proceed next? So do we know values of V1 and V2? So V1 and V2 are known. So volume of this larger rod is known in terms of area multiplied by its length. Similarly, V1 and V2 are known. How do you obtain U1 and U2? So you have to use this equation. Will the stress, so in this case the stress, let's say is sigma 1 and here stress is sigma 2. Will the stress be same in both cases? They will not be same. So let's work out that later on. So U1 will be sigma 1 square divided by 2e multiplied by V1 plus sigma 2 square divided by 2e multiplied by volume of the second component. So how do you write this sigma 1 and sigma 2 in terms of the load which is given? P by A. So for the smaller rod, it will be the load divided by area of this particular rod. For the second one, it will be this multiplied by area of that particular rod. So let's write that. So the first part, this particular part I have written here. So sigma 1 is P, the load on this section is P, divided by area of this cross section, that is n square A, the whole square, divided by 2e multiplied by volume, which is area multiplied by length of this particular cross section. And similarly, we have to write for the second part. So sigma 2 would be given as force by area of the second part, divided by 2e multiplied by volume, which is A into L by 2. And we have to simplify this particular part. So we get n square by A, one of the n square by A term will get cancelled with this n square by A. So we'll have P square multiplied by L divided by n square A divided by 2 become 4, and then you have E. So that is the first term, and similarly for the second term. So we get the final form of the equation. So the total energy content would be given as E square L by 4 L A. So that is the answer to this particular problem. We can verify the answer by comparing with the previous case. So previous case we had a rod which is of total length A and area equal to A. So can you tell how do you convert this problem into other problem? So if you want to convert this problem into that of a rod of uniform length, which parameter would require change? N will be equal to 1. So if you make n equal to 1, then you should get the same answer that we got earlier. So if you put n equal to 1, you will get T square L divided by 2 EA. That is what answer we got in the previous case. So that is the energy method. In the next class, we will look into more interesting case where somebody hits this particular rod. How to calculate stresses in that particular case is what we will discuss in the next class.